Well, my name's Dr. Tim Krantz. I'm a professor of environmental studies at the University of Redlands, and it is my pleasure to speak to you today, to this group of San Benito County farmers and ranchers, with regard to hydraulic fracking, and why it should concern you. Just first a little background on basic groundwater hydrology. We have infiltration of precipitation and surface runoff through the sediments and the surface layers of bedrock into the groundwater aquifer. The groundwater aquifer itself is where the water becomes saturated between all of the soil particles. And groundwater aquifers move up and down seasonally with regard to the availability of those water resources for the surface. In particular, in fracking, the concept is that they drill a well, they can use existing wells or drill new ones, down below the groundwater aquifer into shale, in this case the Monterey Shale deposits, and then they inject into those wells a series of chemicals to try to dissolve that and bring it back to the surface. The fracking process itself involves drilling wells to depths of greater than 5,000 feet, where the well then can be turned horizontally into a system of lateral wells, if you will. And then those are, through a series of small detonations, they can then open those pipes up and actually fracture the shale deposits around the well casing to enable the chemicals in the fracking solutions to dissolve the shale and oil and other materials and be able to slurry that and bring it back to the surface. The first 1,000 feet or so of the well are lined, and this is with the idea of preventing any seepage or leakage of the chemicals back into the surface layers of the groundwater that we would potentially be pumping up for farms and fields and for municipal use. The problem is that within those wells, about 1 out of 7 of those are going to be leaky, and they're going to emit those chemicals back to the surface. Another problem will be that once those chemicals are injected at depth, under great pressure, the chemicals will try to find their way back to the surface. Oil floats on water, and so you're going to get the natural migration of those oil shale components back upwards towards the surface at the surface of the groundwater table, whereupon they will flow downstream below ground, surfacing at either in the rivers or in riverbanks, or where these rivers come down to the ocean. This would be where groundwater comes to the surface at sea level. You may have seen pictures of flaming faucets and other symptoms of groundwater pollution, tap water pollution in fracking areas. These are the volatile components of oil and gas that literally are coming back up to the surface, where municipal wells can then draw those out, and the volatile components of those are flammable. Beginning in the mid-1990s, I worked for an environmental engineering company called Levine Fricke, and we worked on cleaning up oil and gas releases, oil spills, in and around California. I had the opportunity then to work with what's become known as the Exxon Valdez of California groundwater pollution episodes at the Guadalupe Dunes west of Santa Maria. In the Santa Maria area, there was an old oil field there that was no longer productive. And so Unocal began injecting these wells with benzene, kerosene, and other types of solvents to try to dilute and make some of the heavier components of the oil field extractable. Over the period of a decade or so, from the mid-1970s through the mid-1980s then, Unocal injected 12 million gallons of these diluents into the old well field and well casings, but much of that leaked out and then proceeded to float on top of the groundwater down towards the beaches. And here were fishermen casting their lines out from the shore, kids playing on the beach, making sand castles that reeked of gasoline, where the groundwater was coming to the surface right at sea level on the beach. So what to do with 12 million gallons of contaminated groundwater flowing down towards the coastal dunes? Ultimately, Unocal had to remove 400,000 gallons of contaminated sand and water from the beach itself. They then installed an impermeable barrier that extends along the beach here from the back of the four dunes to where this extends down to, was installed down to the groundwater depth, where the oils and volatiles would pool behind it and then would have to be treated and removed at the wastewater treatment facilities that you see here in this aerial photograph. When the oil industry talks about creating jobs and jobs over time, these fracking wells typically exist for less than a decade, often only a matter of a few years before they are capped and no longer productive. Whereas the jobs cleaning up these contaminated groundwater systems will be in perpetuity. The only job security here is in the job industry of trying to clean and maintain these water resources for the next generations. So to summarize the statistics of the Guadalupe Dunes groundwater contamination episode, there were 12 million gallons of diluents pumped into the ground, into the well field. Of this, 400,000 gallons of contaminated sand and water were removed from the beach, and this has indeed created hundreds of jobs, most of those in the groundwater contamination cleanup industry. Altogether, fracking uses a slurry of different chemicals. More than 700 chemicals have been listed as used in fracking operations. Most of these are solvents such as benzene, toluene, kerosene, together with other acids, hydrochloric acid, acetic acid, and so forth, that help dissolve the shale. There are also naturally occurring radioactive materials called by the industry norms, such as radium, radon, uranium, and thorium. These are naturally occurring radioactive isotopes in the Monterey Shale deposits. Add to that tenorms, these technologically enhanced naturally occurring radioactive materials. These are not actually naturally occurring at all, such as manganese 56, technetium 99, xenon 133, iridium 192. These are highly radioactive isotopes that they purposefully inject into the wells so that they can track those using modern, essentially Geiger counters, to track the horizontal movement of their wells to see where they are below. You may have heard of the seismic risks associated with fracking. And these are well documented now, to where areas that are well away from any known seismic earthquake fault areas, such as Oklahoma, have seen an enormous increase, an exponential increase in the numbers of earthquakes associated with fracking. In this particular case, between 1975 and 2008, Oklahoma typically records 5 or 6 earthquakes a year. These are all very small, low magnitude quakes. And yet now, Oklahoma has become the second most seismically active state in the continental United States, second only to California. And this is strongly linked to and is parallel to the increase in fracking in that state. The Seismological Society of America itself recently, at their May annual meeting, had a special session called Induced Seismicity, where they looked at the seismic relationship of earthquake events associated with fracking, and they found that, in fact, The result of fracking was to spread the area of seismic hazard farther out from the fault line. Literally, these diluents and solvents are moving out along the plains of the shale deposits and lubricating those surface areas such that they can promote seismic release. The issue of wastewater is perhaps the most serious one with regard to the farming and agriculture industry. Altogether, 1 to 4 million gallons of water are used per well. And then these are used not only in injecting the well with the water to begin with, but bringing that water up together with groundwater and other wastewater, and then putting those into holding areas, detention basins essentially, where they then separate the volatile components and the oil and gas from the water itself. Then they would either re-inject the contaminated water back into the well case, or hold it and put it into a treatment pond, which hopefully would be which consists of a lined pond that will simply prevent any further leakage to ground. And then ultimately they have to dispose of that as hazardous wastewater. The industry euphemistically calls this produced water. They're not making water, but they're actually bringing up groundwater and the water that they inject into the wells together with oil, gas, and the rest of the chemical slurry that they are sending down in the well to begin with. 1 in 7 of the wells typically will fail in the first couple of years of operation. The leakage in and around the wellhead is virtually across the board. Every single wellhead will have some leakage at the surface where they're spilling drilling muds and other contaminants that they're bringing up. The fracking industry itself will often say that not to worry, that they're drilling at depths that are much below groundwater, but in fact, these low depths are very subject to communication back to the surface. In all of the graphics with the industry, you'll see what they call an aquiclude, or a geological stratum that separates their deep shale-producing, oil and gas-producing stratum from the surface groundwater aquifer that we use for municipal and agricultural uses. But in fact, there are no unbroken geological layers that would separate deeper fracking wells from the surface, especially in California, where the entire geology of the Monterey Shale Basin and San Benito County is crisscrossed with the fault lines of the San Andreas Fault. If you looked at a seismic map, it would show literally a spaghetti plate of fault lines running from southeast to northwest. All of that has so fractured the rocks and the geology of these areas that there would be absolutely no way to preclude contamination and movement of contaminants back up into the groundwater aquifer that we use. There are a couple of laws of physics that come into play here. One is oil floats on water. So as soon as you're releasing these oils and the more volatile components of the gas, these will rise to the surface of the groundwater aquifer, where they begin to flow downstream towards the rivers and towards the ocean. The second law of physics here is that fluids and gas move naturally from high pressure to low pressure. It doesn't take a rocket scientist to figure out where the low pressure is when you're talking about groundwater. Lower pressure is at the surface. And so that's naturally where the fracking fluids are going to end up. In conclusion, I would argue that there is compelling evidence that fracking and other means of enhanced oil recovery, as they call it in the industry, will use millions of gallons of potable water per well. Once contaminated in these groundwater aquifers, they may never be remediated over human generations. That is, our children, our children's children, their children's children will be cleaning this stuff up. And therein lies our real serious problem. Are we willing to commit these groundwater resources to contamination for generations to come? We Californians, particularly the agriculture and farming industry, cannot afford to waste our precious water resources on fracking.